Hello. We have been discussing the problem of omitted variable bias. And in our example of student to teacher ratio and test scores, the omitted variable, one important omitted variable suggested was the number of ESL students. So ESL means English as a second language. So foreign-born students, non-native students, is on like is an important determinant of the test scores. So as it says, school districts with fewer non-native students do better in the test and at the same time have smaller classes. So because they could afford more teachers and so have smaller student to teacher ratio. So the number of ESL students is the confounding variable, but the problem here is you do not observe that. But fortunately, we have the data. So think about this. This is from California data, and the sample size is about 420. So there are 420 school districts, and we observe their student-to-teacher ratios and their uh, test scores. And also we observe their percentage of ESL students. And I am going to interpret this table. Now, this is a real data, the real data. And first, to simplify the presentation, we are going to divide the data into small class and large class. Small class is defined as student to teacher ratio less than 20, and large class is greater than or equal to 20. And as you can see, in small class group, there are 238 school districts observed, and their average test score is 657.4. On the other hand, in the large class group, we have 182 observations, 182 school districts whose average test score is 650. So this is what we learned earlier. We have seen this before, and by a simple calculation, you could see that the difference between small and large class school districts is on average 7.4. So 7.4, so it, like compared to the large class school districts, small class group had a higher average test score by 7.4 points. This was earlier conclusion in the chapter 4, but we learned this could be overestimated. So overestimated because this 7.4 includes the direct effect that we are looking for. At the same time, it may include the indirect effect through the number of ESL students. So we now prepared additional rows which uses the percentage of English learners. So ESL students can be lower than 1.9% and between 1.9 and 8.8 and like that. I don't know why the authors chose this interval. Maybe the data could have maybe data was given in by those intervals, or maybe they just divided the data into four different strata, or I'm not so sure, but anyhow, so let's see what happens. First, as you go down, there are more non-native students. There are more students who use English as a second language. So and then as you go down, more ESL students, and there is a clear pattern in the average test score. So the test score has a clear decreasing trend here. So the first two rows are similar, but clear drop here from here to here, and another bigger drop here to here. Same here. So, and then this is consistent with our conjecture that more non-native or foreign-born immigrant students uh, may result in lower test scores. And so that is a clear pattern in the data. And also, we are going to compare the ratio between these two. So think about the first row where these are the school districts who have very few ESL students, very few immigrant students, and then like nearly 70%, more than 70%, nearly 7 to 3, more than 70% of this few immigrants districts had small classes. So, which means, and on the other hand, think about the ratio. It's 76 to 27, and then 64 to 44, and then 54 to 50, 44 to 61. So there is a clear drop here and clear increase here. So the the proportion of large class increases as the immigrant students increase. That means, which is also consistent with our conjecture, because I assume that more immigrant students, the school districts with higher percentage of immigrant students are likely to be less fluent areas, less fluent districts, so they are less likely to have a small class group. That's our guess, and this pattern is also confirmed by the data. The data also tells the same story. And finally, what is interesting here is now compare the average test score between small and large class groups within the same percentage interval. So if both large and small class groups have very few ESL students, then their difference is actually negative. So larger class group had higher test score, which is surprising. And also, if you do that like for each percentage intervals, so in the second interval, if you calculate their difference, being in small class improves the test score only by 3.3 if provided that the ESL students are only like 1.9 to 8.8 percent point. And third interval has a difference of 5.2, which is the largest among them, and the last group has 1.9. So what we need to understand from here is all of these four intervals generated smaller value than this. It's interesting, right? So this overall difference is not a weighted average of these four groups. You cannot interpret that way. These four groups have strictly smaller estimate than the overall estimate. The main reason is so remember, we expected 7.4 includes the direct channel and indirect channel. But by dividing the data into four intervals, four groups defined by ESL percentage, within each group, the effect of the indirect channel is minimal, because there is not much difference in the percentage of ESL students. So like for example, we are comparing less than 1.9% in this comparison, But in this comparison, you are comparing this to all of these guys. So all the four groups are compared to each of the other four groups. So it's not one to one. So you are and the problem here is, as you see, the proportions are distorted. They don't have the same proportion here and there. So the proportion is distorted. So overall comparison causes the bias, and which is also confirmed in the group-wise analysis, which is really interesting. So this is a very interesting example, and it explains everything is consistent with our common sense. So let's think about this. I explained almost everything, and exactly we have, so by a simple table, I have proven that the fraction of ESL students can be a confounding variable, or if you don't use it in the regression, it can be the omitted variable and causes the omitted variable bias. Therefore, you need to include that, if possible, include that in your estimation, and this is particularly important in causal interpretation. So earlier, maybe I did not talk about this carefully. Earlier, the authors claimed that the regression model is used for two purposes. One is prediction, and the other is causal interpretation, causal inference. At the lower level, they are similar, and it's not so seriously different. Like seemingly, they are similar, but we are going to, from now on, we are focusing more on causal inference. There are a little bit subtle difference in interpretation, but we will lean more on toward causal interpretation approach, because prediction is more straightforward, I think. So please understand that, and later, if I have chance, I may explain why we have to distinguish them. But for a while, it's important. So in this case, the causal inference is done like so. The causal inference we want to do here is, so I am the superintendent of my school district. I'm considering if it's worth hiring more teachers. Then what I want to estimate is, so if suppose that I hire more teachers, and so think about two scenarios: hire more teachers, not. And what would be the difference in the test scores between these two scenarios? Both are hypothetical, imaginary scenarios, but we would like to say something from the data. Okay, we will, so we are going to talk about the approach to this causal inference in the next video. Thank you for watching this. Bye.